Welcome to this lecture video. In this video, I am going to explain elastic properties of materials under the topic elastic materials, which comes under module number 2 of engineering physics prescribed by VTU. Here I am going to discuss the following points, that is strain hardening, strain softening, Young's modulus denoted by symbol capital Y, rigidity modulus denoted by symbol N, and bulk modulus denoted by symbol K, and Poissons ratio, that is sigma. So here let us concentrate on what is strain hardening and what is strain softening. So strain hardening, so when a elastic material subjected to series of stress, it will undergo strain. So stress is nothing but a force per area, and strain is nothing but change in dimension to the original dimension of the body. So if we plot a graph of stress versus strain for a elastic material, the curve obtained is as shown in the graph. So here from O to A is observed to be a straight line. Here stress is proportional to strain, and the point whatever that is B is considered as yield point, okay, and the point C is known as lower yield point. So up to extent B, the stress is proportional to strain, and whenever the force is removed, the material come back to its original state. Beyond the point B, it is observed that the curve will be different, and when we take the slope for that curve, it will going to become negative, and between the point C and E, the material will not come back to its initial state. And the process of making material harder by plastic deformation is known as strain hardening, and the process of making material soften by plastic deformation is known as strain softening. So in case of strain softening, for example, concrete is a best example. So the concrete material becomes softens after some time. So when it is subjected to series of stress and strain, so here stress is proportional to strain up to certain extent, and beyond yield point, the curve obtained will have negative slope. So the process of making material soften by plastic deformation is known as strain softening, and the process of making material harder by plastic deformation is known as strain hardening. So strain hardening is coming to picture in case of metals. Now let us discuss about what is Young's modulus. So Young's modulus is an elastic constant, as according to Hooke's law, stress is proportional to strain within elastic limit. That means stress is proportional to strain. When we remove the proportionality, a constant will come into picture. That constant is known as elastic constant. So when we take the ratio of longitudinal stress to longitudinal strain, the constant of proportionality is known as Young's modulus, denoted by symbol Y. So here Young's modulus is equal to force per area, that is divided by change in length to original length, that can also be written as F by A by delta L by L. Here F is force applied and A is the area of cross section, and delta L is change in length, and capital L is the original length of the material. So finally the Young's modulus of the material can be written as FL by A delta L, so many Newton per meter square. So when a string is subjected to stress, that is when a mass is fixed at one end of the string and the other end of the string is fixed, so the string undergo extension because of the force applied. So let L be the original length, let delta L be the change in length of the wire. Then we can write the longitudinal strain as delta L by L, and the longitudinal stress can be written as force per area. Finally, the Young's modulus can be written as FL by A delta L, so many Newton per meter square. This is what about Young's modulus observed in case of strings. The another concept is rigidity modulus, denoted by symbol N. Rigidity modulus is the ratio of shear stress to shear strain within elastic limit. So shear stress means it is nothing but a tangential force applied per unit area, and shear strain is nothing but lateral displacement between two layers divided by perpendicular distance between the two layers. So here we have to consider a mass which is fixed at its bottom layer, and its top layer is subjected to a tangential force. Then it will undergo deformation and it will gets tilted through a small angle, say theta, known as shearing angle. So the rigidity modulus N can be written as F by A divided by theta. So here the value of theta can be written as delta x by x, where delta x is change in position of the top layer, that is delta x, and x is the distance between the upper and lower surface of the material. So finally, the rigidity modulus N can be written as F by A divided by theta, so many Newton per meter square. So here the value of delta x by x is equal to tan theta, which is approximately equal to theta, since theta is observed to be very small. So this is what about rigidity modulus of the material. So when a body underwent tangential force, so the tangential force per area can be considered as shearing stress. By that time, the material tilted or turned to a particular angle known as theta, that is what is called shearing angle. Okay, so the rigidity modulus N can be written as F by A divided by theta, so many Newton per meter square. The other one is bulk modulus, denoted by symbol K. So bulk modulus is nothing but the ratio of bulk stress to bulk strain within elastic limit. So here bulk stress can be written as force per area, whereas bulk strain is nothing but change in volume to original volume. So bulk stress is nothing but F by A, and bulk strain is nothing but delta V by V. Here V is the original volume, delta V is change in volume of the material. Now we have to consider a material in the form of a sphere. Let V be the original volume of the sphere, and when the sphere is subjected to series of force or compressive force in all direction, then it will be gets compressed. The change in volume of the sphere is, let it be delta V. Then the bulk strain can be written as delta V by V, and bulk stress can be written as force applied per area, unit area. So the bulk modulus K can be written as Fv by delta V into A. So further, the value F by A is equal to P, known as bulk pressure. Okay, it is known as bulk pressure. So we can write the value of K as PV by delta V, so many Newton per meter square or Pascal. This is what about bulk modulus of a material when it is subjected to stress in all directions. So this is what about bulk modulus K. And here the another topic is Poissons ratio, denoted by symbol sigma. So we already know that lateral strain is nothing but increase in length to the original length. Similarly, longitudinal strain is nothing but increase in length to original length, whereas lateral strain is nothing but decrease in diameter to original diameter. So here is a wire of length L and of diameter small d. So when it is subjected to extension whose length is extended to L dash, let delta L be the increase in its length, and the diameter automatically compressed to d dash, and the corresponding change in diameter, let it be delta d. Then longitudinal strain can be written as increase in length by original length, that is delta L by L, and lateral strain can be written as decrease in diameter to original diameter, that is delta D by D. The Poissons ratio sigma is equal to the ratio of lateral strain to the longitudinal strain. So lateral strain, as according to the above equations, it is nothing but delta d by d, and longitudinal strain is nothing but delta L by L. So finally the value of Poisson's ratio sigma is equal to delta D into L by D into delta L. So this is what about Poisson's ratio of the material. So now we discussed about Young's modulus, rigidity modulus and bulk modulus, and hence we are aware of longitudinal strain, lateral strain, and then Poisson's ratio. It is the ratio of lateral strain to longitudinal strain. So that's what you can observe in this slide. Thank you.